2.5, rational functions. So rational functions is something that we've already worked on a little bit this year. We did it last year in Algebra 2 as well. So we're just going to kind of make sure we understand all the different kinds of graphs today and just review everything. So the first thing we worry about when graphing is our x-intercepts. So we let our numerator equal to 0. Our asymptotes come from the denominator equal to 0, which makes sense because we know that if our denominator equals to 0, we have something that's undefined. For our y-intercept, we let our x be 0. The wholes come from factors that you can cancel out, so we do see these sometimes. And I would say that this is going to be removable discontinuity. Removable because if we remove the whole, then it would be continuous. We should also add that when our denominator is equal to 0 and we have vertical asymptotes, that is infinite discontinuity. Because our graph will approach, our function will approach infinity along that asymptote. So infinite discontinuity. And the last part is the y-asymptotes. Those are a little more complicated. It really depends on the degree of the polynomials in the numerator and denominator. So if we have a bigger degree and it's not coefficient, it's not leading coefficient, it's bigger degree. If there's a bigger degree on the bottom, we have y equals 0. If it's the same degree, we're going to make a fraction out of our leading coefficients. And then if it's a bigger degree in the numerator, there's no horizontal. But if it's only 1 degree bigger, we divide out and we can get a slant asymptote. And so we will look at all 3 of these scenarios for horizontal asymptotes because that tends to be the most challenging part for people. So looking at number 1, we're going to do all of that info and then we're going to go ahead and graph and state domain. So I always want to start by factoring so I can get a good look at the function and make sure we don't have any holes. And then my x-intercept I will get by letting my numerator equal 0. So I'll have an x-intercept at -1. I'll have a y-intercept by putting in 0 for my x's. So I'm going to go back up to the top and make it 0 plus 1 over 0 minus 4. So -1/4 for a y-intercept. For my x-asymptote, I will need to let my denominator be 0. So there'll be 2 x-asymptotes. So for x-intercepts or asymptotes, there can be more than 1. For y, there's only 1. So x plus 2 is 0, x minus 2 is 0. So 1 at 2, 1 at -2. And for my y-asymptote, let's go back up and look at those degrees. So my numerator is first power, so it's linear, and my denominator is squared, so it's bigger on the bottom. And so it's y equals 0. So now I'm going to put all that info into my graph, and then we'll figure out how to connect it. I think I'm going to do everything in blue, and then I'll go back and do the graph in a different color. So my x asymptotes, let's do asymptotes first. So I have an x at -2 and an x asymptote at +2. And a y asymptote at 0. And then I'm going to make a little bit of a scale. All right, so now let's actually graph our function. Let's see. So my y-intercept is a -1/4. And my x-intercept is, oops, if it's x plus 1 equals 0, it should be a -1, shouldn't it? So we'll go ahead and fix that, -1. So now I know I need to draw this graph. I can cross my horizontal asymptotes, and evidently I do because I do have an x-intercept. And I know I have to cross it in a way that it makes a curve, a smooth curve, and it has to hug those asymptotes. So I'm going to go ahead and graph the middle part. So I'm really confident that's the way that one looks. Now I know that for the other pieces, our graph alternates, right? I'm not going to have part of it here and up here. So I could go ahead and check, this line is x equals -2. I could check like x equals -3 or -4 and figure out if it's up or down and do the same thing over here. But after you graph enough of these, you really kind of understand how they work. And I know that my graph over here is going to have to kind of run parallel to this part of my graph. It's going to go like this. And the one that's on the right is going to go like this. So again, I've just graphed a lot of these. I kind of know how it's going to graph. If you're not sure, you could check a value over here in this region. So you could check like x equals -3, and you could check x equals +3. So you are welcome to do that, but I am not mandating it one way or the other. The goal is that we get really good and we understand these graphs so that we can just quickly draw something and have a picture in our heads. The goal is not perfect, complete accuracy with lots of points. The goal is, where is the graph above the x-intercept or x-axis? Where is it below? What's going on? Last thing we were supposed to add here was our domain, which I almost forgot. So our domain goes from -infinity to that line, right? We have infinite discontinuity at the line to -2. And so those are both soft parentheses. And then it goes from -2 to 2. This is a U for union. I've heard that in calc, a lot of times it's just like a comma between the two. And then it goes from 2 to infinity. So that's going to be our domain. All right, for the second one, like I said, I always like to factor my functions first. So this will be an x minus 4 times an x plus 3. Oh, look, it's x minus 4, x plus 4. So what we can do is this is going to create a hole. If I think about x minus 4 equaling 0, it would be x equals 4. So we are going to have a hole at x equals 4. But we can graph that reduced function, x plus 3 over x plus 4. So we're going to graph this instead, but we've got to remember that we have a hole at 4. So we have an x-intercept from our numerator, x plus 3 equals 0, x equals -3. We have a y-intercept from letting all of our x's be 0. So 0 plus 3 over 0 plus 4 is just going to be 3/4. I have a y-intercept, or I already did y-intercept. I want to do x-asymptotes is what I want to do. So my x-asymptotes come from my denominator. So if x plus 4 equals 0, I will have an x-asymptote, a vertical asymptote at -4. And then our y-asymptotes. So I know that I have the same degree equation on the top and bottom. My numerator is x plus 3. My denominator is x plus 4. They are both linear. They are both x to the first power. So I need to take those leading coefficients and I need to make a fraction out of them. So 1 divided by 1. And so y equals 1 divided by 1, which is just 1. So our y-asymptote is 1. Now we're going to put it all together again. Let's see, I need a -3 as my intercept. -4 would be my asymptote. And then let's see, y equals 1 is my y-asymptote, my horizontal. So now I'm going to go ahead and plot some points. I have a point at 3/4. I have a point at -3 on my x-axis. And then I want to go ahead and connect them so I can see clearly what's going on here. I'm going to have part of my graph on this side. And then remember, these are always alternating. So I'll have part of my graph over here. But I do need to add in that hole. So at 1, 2, 3, 4, I have a hole. So that means where x is 4, I'm going to go up to where my graph is. And I'm just going to draw a circle to show a hole. So now to write my domain. So I know that my domain will go. This graph keeps wanting to jump around. Maybe I'll write it above. My domain is going to be from -infinity up until my my asymptote, that's where I have infinite discontinuity, so that's at -4, union, and then from the line to the point, right? So from -4 to 4, because at 4 I have a hole, union, and then from 4 to infinity. And I'm using soft parentheses for all of those because I can't actually include -4 or 4 because I have an asymptote, I have a hole. So for 3, we're trying to graph again. I need to go ahead and factor first. Really, we're looking for holes when we do this, but it also gives us a better idea, puts us a step ahead when we go to find asymptotes or intercepts. So my x-intercepts come from the numerator. So x plus 4 times x minus 2 equals 0. So either x plus 4 equals 0 or x minus 2 equals 0. So the x-intercepts are -4 and +2. My y-intercept comes from letting all the x's be 0. So I'm going to go back to the beginning and have 0 plus 2 times 0 minus 8 over 0 minus 3. So it's just -8/3, which is -2 and 2/3. It's going to help for me to have that as a mixed number, so I know exactly where to graph it. Let's see, I have x asymptotes. I guess just one here from the denominator. So x plus 3 equals 0, x equals -3, and then I need to worry about my y asymptote. So to do that, this time I see that I have a bigger degree on the top. So my numerator is squared, my denominator is first power. So it's bigger in the numerator and it's 1 degree bigger. So because it's bigger on top, so let's go through all the steps. That means no horizontal. Okay, but it is 1 degree bigger. 1 degree bigger. So that means in this case, I'm going to divide to get the slant asymptote. So I have to take the numerator and just literally divide by the denominator. So my numerator was x squared plus 2x minus 8. And my denominator was the x plus 3. Let's just double check that really fast. So I could do long division. Is that right? X squared? Yep, that was right. But easier in this case because I'm dividing by a linear factor, I could actually just use synthetic. So synthetic would mean I'd have a -3 out here, and then my coefficient 1, 2, my constant's -8. So we'll go ahead and do our synthetic. So you could definitely still do long division, but it's not necessary. For our slant asymptote, we throw out the remainder. And this is not always, this is just when we're finding a slant asymptote. And this is going to be our equation. And so remember, if we started out with squared, then this is a 1x minus 1. And I'm going to put the 1 there just so it's really clear. So x minus 1 is going to be our slant asymptote. So we say slant asymptote because it's not a horizontal or a vertical line. It has a slope of 1. It's going to be slanted. But it's still going to function like a regular asymptote would. So let's go ahead and get some stuff down on paper. Let's see, we had intercepts at, or sorry, not intercepts, asymptotes at 2. And we had an asymptote for x at -4, so another vertical one at -4. Oh no, wait a minute, those were our x-intercepts, shoot. All right, let's start over. This happens, right? So let me go ahead and mark 2 and -4 so I don't forget what I'm doing. And while I'm at it, let's do our y-intercept at -2 and 2/3. Okay, so that's all my intercepts. Now I've got to worry about those asymptotes. So my asymptote was at -3. And the other one is at that slant asymptote at y equals x minus 1. So here's the -1, and then a slope of up 1 over 1 is going to look something like this. So I'm just trying to do the best graph I can. All right, so now I know my graph needs to hug those asymptotes and go through the points. So this one's pretty obvious, right? It's going to go like this, and this one's going to go like this. So we've got our graph. So now we've looked at all those different kinds of situations for horizontal asymptotes. We looked at none where there's a slant. We've looked at y equals 0. We've looked at having to make a coefficient out of the, or fraction out of the coefficients of those leading terms. We've looked at all those situations. Our last problem is actually not graphing. It is just solving. And our strategy is going to be to multiply to get rid of the denominator. So we're not going to work with fractions. We're going to get rid of fractions. So I am going to multiply both sides by x minus 1, because that is going to quote unquote cancel my denominator out. So when I distribute x minus 1 times x, it's going to be x minus 1 times x. When I multiply the x minus 1 times the fraction x divided by x minus 1, we've got that common factor. We're just going to be left with x. Because when I have a common factor in the numerator and denominator, it just basically I'm dividing it out. It's a 1. And then over on the right, same thing. We have a 3x minus 2. So now I'm going to distribute x squared minus x plus x. And then let's see, this is just x squared. I want to get everything on the same side as x squared. So we'll have x squared minus 3x plus 2 equals 0. So the 3x was positive. I had to subtract. I had to add 2 on both sides. Go ahead and factor. And then I'm going to solve. So either x minus, oh, this should be x minus 1, x minus 2, shouldn't it? -2 times -1 is 2. Add them, it's -3. So either x minus 1 equals 0 or x minus 2 is equal to 0. And then I don't have to worry about a lot with fractions, but I do have to worry about denominators equal to 0. So I need to go up to the first step and make sure that 1 and 2 are both okay. So if I put a 2 in my denominator, 2 minus 1 would be 1. I'm allowed to have denominators of 1, no problem there. But what if x was equal to 1? If I had x equal to 1, I'd have a 1 minus 1 in my denominator. So this is going to be an extraneous solution, because I cannot have a denominator equal to 0 even in the original problem. So my only answer here is going to be x equals 2. So one last thing that I want to add before I sign off here and we're done with these notes is that I did not do domain in the last problem. So just to quickly add that domain piece in, my domain would be from -infinity up to that line, which was at -3. And then, oh goodness, this is kind of tricky here, right? So at x equals 1, we have a break again. So from -3 to 1. And then from 1 to infinity. All right, I think we're all set.